So last time we began talking about biogas, and we will continue with a few more things on biogas and then move on to ethanol. Now, let us look at the advantages of biogas. I think we did cover a few last time, but let us try and put it again, all together. First is that, there are a wide variety of bio feedstock, including waste streams, from which you can derive biogas. That's so in that way it's quite nice because you can look at a variety of feedstock. Of course, it is a bio process, which is an advantage. You don't need any chemical processing, okay, in making biogas, which is also important. And because it's a bio process, it's under ambient condition process. So that's again a big advantage, okay. Now, in many of these cases, what you'll find is that after one gets biogas, then the rest of the material that is left over, the sludge and liquid effluent, actually it's quite a good fertilizer. And not in all cases, but in many cases. Okay? So actually you can make use of it. Provided, of course, there are no harmful things which have got generated in the process of making biogas, which can happen. Like, for example, if I invariably will form some H2S, and if that H2S is not removed, then it can harm the plants. Okay, so it's good as a fertilizer, but one needs to be careful. Because it is a fairly simple process, and which gives you a high value product, especially cooking gas, it's very amenable to decentralized production. I mean, you can, because we generate waste all over the place, okay? And so there's no need to bring it to a central factory. You can actually set up small biogas plants, and that's nice. It's even small communities can do it. Housing societies can do it if they want. So you can actually have decentralized production. You even let's say companies that process fruit, say fruit juice and things like that, and you have a lot of waste materials, which can ideally be converted into biogas. Okay, it's not capital intensive. The capital costs are very nominal in a biogas plant. It's easy to trigger. Most of the time, you need just something like a little bit of gobar, or something, and you can actually trigger the biogas production. Okay, and not in all cases, but in many cases, you can actually use it directly without any purification. Although in more demanding applications, you'll need to purify it. I mean, you cannot use it like that. All right, but in many other cases, you could. I mean, if you're not particularly finicky about certain co-products, then you can burn it. You don't actually, it doesn't, and in any case, when you're burning it, those things will also get burned. So it's not too bad, but it's something to make a note of, that there are impurities there. Okay, it's not just methane and carbon dioxide. Now, let us look at the kinds of solid residuals. This is, of course, where you have got solids, all kinds of, fruit waste, municipal solid waste, okay, animal manure, okay, food processing and agricultural residues, of all kinds, okay. So all of these things can actually be processed for biogas. Otherwise, many times you just don't know what to do with it. Although, I mean, one of the things, of course, is that many of these things are good as manure. So you can put it in agricultural fields. but sometimes, I mean, the agricultural fields could be far away from the point at which you're producing it. So it may be better to convert it into biogas in those cases. Now, when you look at, let's say, something like a carbohydrate or a sugar going to methane, uh, how many electron processes that? What would be the change in the oxidation state of carbon? Say going from, say, sugar to methane. What is the oxidation state of carbon in sugar or starch?
Zero, sir.
Zero, right? And in methane, how much is it?
4.
Yeah, you know, I mean, actually it is -4, not +4. Okay, because H we take as +1. Okay, so you are actually going, from something like a zero state to a -4 state. Now, obviously, there are 4 electron processes, and for those who are not so familiar, I mean, it's not sometimes so easy to convert from something like a, oxidation state of 4 electron change. So usually they will proceed in sequence. You won't directly get methane, okay? And the intermediates, typically two of the intermediates that are formed, one is bicarbonate, and the other is acetic acid. Okay, these things tend to get formed. So, for example, if you take this equation, glucose going to methane plus bicarbonate. Okay, and also you can see the free energy change. Naturally, these are spontaneous processes. Otherwise, it will not form. Okay, you are just putting in gobar to initiate it. But other than that, it's a spontaneous process. But then there are certain reactions which could also be non-spontaneous, like these ones. But we'll focus on these spontaneous reactions, okay? And so what you can see is that typically acetic acid and is a intermediate, okay? You get, and then acetic acid is further reacting with water in presence of the enzymes in the initiator, okay, and it is getting converted into methane and again producing bicarbonate, okay, and you can see also how bicarbonate and another molecule that it will form is hydrogen, so you are forming acetic acid, bicarbonate, and hydrogen as the 3 intermediates, and then acetic acid is reacting to form methane and bicarbonate. The bicarbonate in presence of hydrogen, this is the hydrogen that is being formed, okay, it gets converted into methane, okay, or you can also have it stepwise. It first goes to acetic acid, and from acetic acid again you'll get to methane, okay. So these are essentially the types of reactions, which take place in a biogas digester. Okay, so that's what you have, and I think it's important for you to at least note the some of these reactions. Okay, the first 5, for example, and just remember these. Now we saw that there are many solid waste which have to be converted into biogas, and there are also liquid waste streams, and we'll discuss one of those liquid waste streams later on. Okay, and so you need different kinds of digesters, for the solid waste and for the wastewater, the liquid waste. Okay, so just keep that also in mind. And now, what you can see is that many times, when you have got an effluent treatment plant, okay, and the effluent treatment plant will produce some sludge, okay, and that sludge still has a fair amount of organics, okay, which is present. Okay, so this is like what will happen is that if I've got raw water, and then I do an aerobic digestion in an aeration tank, most of it, of course, will get go off as carbon dioxide. Okay, but some amount of sludge formation will be there. Okay, when I clarify it, and then the rest of it, is like my treated water. You may be able to recycle that water, or you might have to discharge that water. Okay, and this solid, because it still has some amount of organics, which is present, so you could actually take that and now do an anaerobic digestion, okay, of this sludge, and generate biogas. Okay, so that's what you can see, sewage, and the advantage is that the sludge is always wet. Okay, but it doesn't matter because the biogas process is a wet process, so it doesn't matter even if it's wet, right? So you can initially thicken the sludge, and then basically carry out an anaerobic digestion. You get your biogas. You can treat that biogas, okay, and upgrade the methane that you get, okay, and then the digested sludge, you can again dewater it, all right, and you might be able to recover some water from that, right, and some of this sludge can actually be quite rich in minerals and things like that. Not always, okay, it can also be harmful, but some of the sludges you could perhaps dry and compost, and maybe it could find an application in the agricultural fields. Okay, but then if there are toxic constituents in the sludge, then of course what you need to do is after this you'll probably have to incinerate the sludge, because otherwise it will be treated as a hazardous waste. Okay, so keep that in mind. Okay, now let us look at some of the cattle waste, or the animal waste, which have got good potential. One is, of course, cattle. I mean, we've got, we are probably the largest producer of milk in the world. So there's a lot of cattle and cattle waste. Of course, cattle waste is a very good fuel and manure, in many cases. Okay, but people have also used it to produce biogas. Now you can see, and typical cattle produces about 10 kg of waste per day. Buffaloes produce something like 15 kg of waste per day, and from each kg you can get about 0.36 m cube of gas, okay, per kg. So you're talking about something like 3.6 m cube from one cattle. Of course, you have to also remember that these are obviously under normal temperature and pressure, and so biogas will have 22.4 liters of volume, okay, and plus it's not pure biogas. There'll be, you can see it's a fair amount of carbon dioxide which is present. So in terms of actual weight, it's not that much, but in volume it is a large volume. Okay, I mean, sometimes these numbers look quite impressive, except when you convert it into kilograms, then they don't look so impressive. Okay, so and again, piggery waste, chicken waste, because we have got massive poultries today. Poultry farming has become a very organized activity today, and there are poultries with God knows how many lakhs of chicken, and so they are all generating the waste in a very concentrated in one area, so it's really wonderful for those kinds of companies to get this kind of biogas. Actually, one chicken doesn't produce much waste, but then if you consider that there are lakhs of them, then it becomes a very sizable amount, and even human excreta. Okay? So if you look at the biogas composition, I mean, you can see this is actually percent by volume. So it will be about 50 to 75%. CO2 is this much. You can see little bit of nitrogen because there is some air which is always gets in. Okay, very small amounts of hydrogen, substantial amount of H2S, and this is the problem with biogas. The H2S formation that takes place under anaerobic reducing conditions. Now, just to look at the heating values, the lower and upper heating values. So here they have given the lower heating value. All right. So you can see a biogas, 60 volume percent methane, which is not very different from this 50 to 75. So it falls in that range of 60, and 40 volume percent CO2, which also falls in this range. Okay. So you can see that, right? Now, what happens is that if you look at the lower heating value, which is uh, the uh, the the net calorific value, all right? What you find is that it's about close to about 18,000 kilojoule per kilogram. Okay, but if you take pure methane, it's 50,000. So it's almost 3 times as much. Okay, of the raw biogas. All right. So here it is about 3 times, whereas you're just going from a 60 volume percent to a 100 volume percent. Can someone tell me why there's such a big change in the calorific value of the pure gas? Well, if you look at, it sounds, as I told you, by volume, it looks large. But you see, if I've got all gases, irrespective of the molecular weight, 1 mole is 22.4 liters. So CO2 has a molecular weight of 44, right? 12 plus 32, 44, whereas methane is just 16. Right. So even though it is 60 and 40, by weight, this is much more. The bulk of the weight is the weight of the CO2. Okay. Now, when I'm removing that CO2 and I'm getting pure methane, naturally, and these calorific values are expressed per kilogram. It is not per liter or something. Okay. So you can see that as it will become quite large, especially when you're talking about 1 kg of this, because 1 kg of this, will have this amount of calories, whereas 1 kg of this, 44 divided by 60 is the weight of CO2 in 1 kg, and 16 divided by 60 is the weight of CH4. So that's the reason why when you upgrade it, there is such a massive increase in the calorific value. All right. Now, this is very important because if you're going to move biogas around, from one place to another, then obviously you only want to move a fuel which is rich in calorific value. Otherwise your transportation cost would be very high. If you had to move, 1 liter of raw biogas as compared to pure biogas. Okay, so there is an advantage, in upgrading the biogas and trying to make it basically like neat methane. Okay, so obviously to do that, one would then have to develop technologies, or those things have to be present whereby CO2 can be separated out from methane, right? So that's very important, and lots of processes have been worked on, right? Like for example, There are chemical processes like I can react carbon dioxide with amines, like triethanolamine, okay, or diethanol amine, because that is basic and CO2 is acidic, weakly acidic, but it's acidic. So it will form a salt with the amine, and you can take it out, and you'll only then get methane. So that's one way of removing CO2, or you can also use adsorbents. There are certain adsorbents which will strongly absorb CO2 and let the methane go by. Okay, or there are membranes, which you can use, which will allow one of the gases to pass through and not the other. You can also do cryogenic separation. So if you cool it down, you can actually separate the gases out, right? So there are various ways in which one can do it. Now, another very interesting thing is that if you do not separate it, okay, suppose I say that let it be there, like for example, I can burn it straight away as biogas, but even otherwise, what else can I do if I have the methane and the carbon dioxide together? Well, I mean, if you leave them together and take out all other impurities, then actually you can promote this reaction. This is the reaction between carbon dioxide and methane to form syngas. Okay, and it is known as CO2 reformation. Okay, so once you get syngas, we have seen syngas is a very powerful fuel. You can put it in internal combustion engines. You can make all kinds of chemicals out of it. So a very nice future application will be really to clean up the biogas, to get rid of other impurities, but to leave the CO2 and the methane behind, and then actually react them so that you are forming syngas. Is everybody understanding? Did you understand?
Yes, sir.
Okay, all clear, right? Okay. Now, let us try also and understand. I mean, apart from your methane and CO2, what are the other things that can come into biogas, and which can have harmful effects, right? And also, where are they coming from? So, for example, you'll always find some amount of moisture will be there in biogas, and if you're not careful, that moisture can cause corrosion. Okay, so corrosion is a big problem, and of course the water is coming from your organic matter, and as it is decomposing, it's releasing water. So if water is very harmful. And so one should try and do it. You can, for example, cool it down, below the dew point, and it will liquefy, or you can compress it. And by compressing it, increasing the pressure, you can liquefy water, even when its vapor pressure is low. Okay, and or you can use an adsorbent and try to take it out, like molecular sieves or something like that. All right. So there are a whole host of methods which you can try and use. And of course, for the specific application, you'll have to see which of these methods is best for you to use. And that will depend on the selectivity of water separation as compared to all other things that are present. Now, H2S will typically come from sulfur-containing amino acids, and so those are the ones under reducing condition will give you H2S. Now, H2S is also acidic, okay? So it's corrosive, right? And it's also very toxic, H2S. So there are ways, like for example, I can take it out as some insoluble sulfides. There are many metal sulfides which are insoluble, so I can precipitate it out, okay? Or I can do an adsorption, maybe even with activated carbon, right? or I can treat it further biologically, but there's no limit to doing this. And I think that one of the things that you must always see is which is the cheapest thing to do and the best thing to do. Okay, most appropriate thing to do. I mean, just because, say, if you're a biologist, don't try to direct everything towards biology and say all my processes must be bioprocesses. Not required. Sometimes a precipitation technique or adsorption technique might be the best approach. Okay? Now, then of course you can have also there will invariably be some air, and there will be oxygen and nitrogen which will come in, and now that you can of course again remove with adsorbents. Those are probably the best to use. Ammonia, obviously there's so much of nitrogen in all the proteinaceous material, and so they also need to be separated out. In fact, this is a many times a difficult job, separating out the ammonium, especially because ammonia is alkaline, and say something like H2S is acidic, or CO2. If it is CO2, it will form ammonium carbonate. It may not. It may, you may be able to take it out, as a solid. Okay, but if the ammonia is very small in concentration, it may not separate out. Okay, so keep that in mind. And again, when you're using municipal waste, there could be deodorant, shampoos, etc. They have silicon containing materials, and then those things can lead to a coating of silicon dioxide in your reactors, etc., and it can cause problems. And finally, of course, there can also be particulate matter, and any particulate matter can, by friction, it can lead to wear and tear of your reactors, right? So you need to have a mechanical filter to separate it out. Okay, the same thing basically is shown in a more structured way, and what you have to decide when you adopt this kind of cleaning operations is what are you going to use it for. That is something you have to first decide. Okay. Now, for one thing is for sure that as the complexity of the process and your purity, is going from say left to right. Okay, and you can then use it in more demanding applications. Okay, if you have made your biogas very pure, almost like CNG, compressed natural gas, that would be great. Okay, but many other cases, if you, for example, choose to make producer gas, as I told you, which is H2 plus CO, which you can get, you may want to use it for its combined heat and power type of applications. Okay, you can use it in an internal combustion engine. Okay, in many cases you might actually remove some of the impurities and actually produce biochemicals out of it. From the methane, we can do it as we said. I mean, for example, once you made syngas, you can make all sorts of chemicals out of it. If you have removed all hazardous stuff like H2S, etc., you might also be able to use it in a fuel cell, where you are generating electricity, okay, from methane. Or if you have got rid of CO2 and everything, and you've got relatively pure methane, nothing as nice as being able to compress it and put it into cylinders, and sell it as fuel. I mean, that could then be a direct replacement for CNG. In fact, just today, someone wrote to me from the US, an old friend of mine, that they are now trying to see if some of the pipelines, in the US can be used for transporting biogas. So obviously there are plans to generate biogas in very large quantities, and he's looking after a national project, related to this. And so, there are very interesting things that one can do. Now, storage is very important. Remember, it's a gas. Advantage is that it comes out as a gas, so I don't need to invest so much of money in taking out the product from my solid or liquid stream. That's a huge advantage. But having said that, the gas will need to be contained unless you have a continuous generation and use. That's possible in certain cases. So you may actually need to store it. Now we saw, you remember that huge bag that we saw. In many applications, you might actually don't require high pressure storage. You can do a very, very low pressure storage, something like 2 psi gauge pressure. That's all. Very, very low. In which case, I can also use extremely low cost materials, some plastic sheet based materials, which I can convert into these kinds of storage tanks, because I don't need high pressures. Medium pressure would be like 2 to 20 bar, so you're talking about 2 to 20 psi. So you're talking about maybe about something like 14 bar maximum pressure, so there you can use the typical cylinders that are used for transporting propane, at about 250 psi, because it's in that range. So these cylinders would be ideal, provided you have got rid of the H2S, because otherwise the H2S can be harmful. And then if you've got very pure biogas, like biomethane, effectively, just CH4, you might want to actually store it under very high pressures. You can see 2000 to 5000 psi. Divide that by 14 and you'll get an idea. You're talking about something like 200 bar to about maybe 500 bar or thereabouts. Okay? So you need to then look at this, and these would be the kinds of things which you might use in your vehicles. Okay, those kinds of instead of the CNG, you just use bio CNG. Okay, with that we have come to the end of biogas. All right, and now what we'll do is that we will start discussing about ethanol. Okay, bioethanol, right? And bioethanol is of course extremely being much talked about. Ethanol, as you know, is a very important industrial solvent. It's consumed by human beings in large amounts. Liquor business is a very big business. Okay, and all of it is bioethanol. And of course, the latest thing is talking about basically fuel, and ethanol for fuel. Now, what is important to know is that if you take, for example, say, suppose I can like in plants, right? Plants can store sugar. Many plants like sugarcane. In many cases, like starch, etc., plants can store sugars, not as sugars, but as polymeric forms like starch. But also relatively not that difficult to again hydrolyze into sugars. And then we saw like plants can also they produce cellulose. Okay, especially we saw that if you have some sterols and things to direct the polymerization, then it can form liquid crystalline polymers, and you can form cellulose or lignocellulose. Okay, and so all of these are effectively polymeric forms of sugar, and sugar, of course, is the monomer. Okay? Now, what typically happens, we all know, like for example, suppose you're looking for some crop, and you get that crop. It could be an oil seed or some rice grain or whatever, and the rest of your mass is basically mostly lignocellulosic mass, and most of the time, as we know, they are just being burnt. Okay, and we saw, of course, that they can be baled, and you can. There are companies that produce fuel out of it. Okay, but one thing is for sure that if you go from let's say sugar towards starch and then cellulose, you know, the cost of the feedstock comes down, comes down very drastically, and at a point where these things are just lying in the field, it might have zero cost. Finally, of course, whenever you go to use something, it is no longer zero cost, people will ask money for it. Okay, but otherwise, it is as good as a zero cost. So I gain, in terms of my cost advantage when, for example, I move from sugar to lignocellulosic biomass. Okay. But the problem is that to convert it into ethanol, the technical complexity of doing that goes in the opposite direction. So it is easiest to do with sugar. Next is starch, and the most difficult is cellulose. So while it sounds great, and people will talk about lignocellulosic biomass, there's so much of this stuff everywhere, and we must make use of it. Okay, all that is great, and I'll show you also technologies that were developed by ICT and pilot plants. Fairly large pilot plants, something like 10 tons per day production was set up. And they were considered very promising. Okay, but when you look at the economics of it, it doesn't look that good. Okay? Technical complexity goes up, and economic viability also comes down. So economic viability will go this way in terms of processing viability. Okay, and feedstock cost will go this way, and technical complexity will climb up. Okay, now the people who have been real pioneers, in the area of ethanol for vehicles is really Brazil, and not just today. Brazil has been at it from 1931 when they ran some of their cars with ethanol. And for those, who may not know, Henry Ford, who made these cars, petrol cars in the US, Henry Ford actually ran his car. This one you can see, it was run on pure ethanol. This car. Now, the same kind of thing, was there with Mercedes and Daimler, Daimler-Benz. When they ran the first vehicles, okay, but they used actually oil, like today, of course, we'll use diesel, but they use things like rapeseed oil and neat oil, vegetable oils. Okay. Now, today you cannot do it because the engines today are much more advanced, very, very high-tech engines. Today, in fact, the engines are high-speed engines, whereas all of these were low-speed engines, and low-speed engines, they are not as sophisticated. The nozzles, etc., through which the fuels passed are not so fine. Whereas today, if you try to run things on that kind of fuels, there are problems. There's another problem with ethanol, that the calorific value of ethanol, is much lower than the calorific value of gasoline. So what happens is that even if you pour, say, 10 liters of both, this is not going to get you very far because the ethanol calorific value is so low, and that's the reason why it's not so easy to run today's vehicles, with neat ethanol. But people have done it. I mean, I'll show you. Brazil has been doing that. They can actually use 100% ethanol, almost the same way that Henry Ford had done. Okay. Uh, now, and these were shared by this person, Professor Horta. He was a very probably in Brazil one of the leading authorities in ethanol production. And we were doing some work together, I for India and he for Brazil. And that's how we got together, and he shared his all his data, and his presentations with me. Okay, and now by about 2005, Brazil had reached about 25% ethanol, and today actually they also can run it on 100% ethanol. Although majority will be around between 25 and 30% ethanol. That would be the kind of blending. Okay. Now, in fact, just to so that you know the Indian perspective, all right, what it was until recently. Okay, and I've probably referred to this, and I'll cover it a bit more. Um, that um, there are two scenarios for ethanol production. The most common, of course, was making it from molasses in our country, right? And not only molasses, it was being made from what are known as exhausted molasses or sea molasses. And the definition of sea molasses is, when something, the mother liquor that you get, is such that even if I evaporate more water out of it, no more sugar can be taken out. So obviously, no more sugar can be taken out as sugar. So obviously, it does not have much value for pure sugar production at that stage. Of course, there are alternative technologies, like you can do solvent-induced precipitation of sugar, but then they have their own problems. I'm not going into it. And these molasses, typically for 1 ton of sugar, if you produce, you can produce about 78 liters of ethanol. Okay, if you look at it from the sugar cane point of view, because sugar cane, 1 ton of sugar cane will give you about maybe about 120 kg of sugar, thereabouts, 100 to 120 kg of sugar. So on a sugarcane ton basis, the value will be about 8.6 liters per ton of sugarcane, whereas per ton of sugar it is about 78 liters. So not too bad. You're talking about something like about maybe about 6.5% by weight, or as a weight percentage of sugar will be about ethanol. Now, Brazil, is a different country, and it's a country with a very large uh, area, very compared to us, the population is much less, very fertile, and so Brazil actually were cultivating sugarcane, not so much for sugar, because their requirement is also limited. Okay? Although they export, of course, a lot, but they were doing it really for as a fuel substitute, really for substituting gasoline use. And so, now what happens is that their productivity is quite good. They get about 75 tons of sugarcane per hectare, and they can produce about 80 liters of ethanol per ton of sugarcane. Now that is not so different from ours, 78, 80, similar. Okay. Now, so, and this is the figure when they produce it directly from sugarcane juice. That means they crush the sugarcane, get the juice, and they don't recover sugar and then make molasses and then make ethanol out of it. They, of course, they will do some, but majority they will just produce it directly from sugarcane juice, which contains about roughly about 18 to 20% by weight of sugar. So it's quite a lot of sugar, and so they say, why should we do all this? Let's just make ethanol. Now, as I said, I mean that was illegal in our country till 2018. Okay? Till 2018, you had to produce all ethanol from sea molasses. Okay, and but then in 2018 they changed the policy. Okay, and so this was the 2018 biofuel policy, and what they said is that there is also another grade of molasses called B molasses. B molasses is like I do one crystallization, I take out sugar, and then I again evaporate and get another crop of sugar, and then whatever I get is called B molasses. Okay, and then I can aim for a third crop, and after that it's exhausted molasses. So the B molasses was being used. So B molasses obviously had more sugar than C molasses. So they initially allowed ethanol production from B molasses, and later on, they have now allowed it directly from sugarcane juice in India. Okay, so again we'll see what it means. Okay, and they also said that in our godowns, there's a lot of crops that tend to rot, and maybe because of mice and rat and things like that. So a lot of crops get damaged. Okay, a lot of potato, corn, etc. gets spoiled. And also apparently in India now we are producing so much of food grain. I hope that is true. That there is a surplus. Okay, so they are trying to divert it for sort of energy production and basically for ethanol production. Now, the policy, of course, also states the production of ethanol from other resources, not just sugarcane. And I talked to you about lignocellulosic biomass, and also of things like algae, seaweed, is based on a technology that we have developed, several years ago, and maybe I'll cover that briefly. All right, so that's what it says. Government allows mills to make ethanol directly from sugarcane juice and bee molasses, okay, which was illegal before. So you can also see, that it's not about this technology. There's a lot. I mean, when we are talking about renewable energy resources, actually things which were not considered as resources before are now considered as resources. Okay, so policy plays a very profound role. But I don't know. I mean, there is a lot of concern that India, with such a large population, and especially when you have years of drought, every year will not be a happy year. We have a frequent droughts in our country, and also, I mean, excessive growth of crops for fuel can also spoil our agricultural fields, our groundwater, because of excessive use of fertilizer and pesticides and things like that. Okay, so there is a food versus fuel debate, but surprisingly, I mean, it seems that the government has given it a miss. They seem to have ignored it. Okay? I don't know. Maybe they know better about availability and things like that than let's say I would do. Okay, but I can tell you this much, that this article is just from today's Times of India. All right. I put the link. You can read the article, and it says ambitious ethanol plan sparks food security fears in India. You know. So there are a lot of people who are actually also criticizing the policy. That is this the right policy for India? You know? And are you really sure that you want to divert sugar production for fuel? Because fuel, I mean, the way people have been, hey, just go for a drive, let's drive. Okay, that kind of an attitude towards energy conservation, the zero kind of consciousness about things like that. And so, whereas if our sugar prices go up, the poor will suffer. They will not have sugar to eat, or they'll pay through their nose. Okay, so just keep this in mind. It's possible that it's a good policy, but only time will tell. Now, let me also tell you that you can see that these are all email correspondences which are quite recent. 17th of September. This person is probably the most important expert in Brazil, in the area of biofuels. Okay, a very senior person, and so he was interested that basically that if he can write an article, and basically an article on about production and use of fuel ethanol in India, and he says that I think this will be a paper of great impact. India and Brazil partnership can create a great impact not only in bioenergy but in economic terms worldwide. Okay, except that I think we need to understand that the two countries there are differences. Okay, we have many similarities, but there are differences, as I told you, in the land area that they have, the fertility of their land, and their availability of water, fresh water, and population, being much less than India. So, while it seems like a good thing for India to go the Brazil way, but there could be issues. Okay? And he then reiterates the point that this was said because what has happened is that there have been a number of articles in India about that if you try to put too much of ethanol into petrol, that people are finding that the engines are wearing off, that there are lots of problems with their engines. Okay, and so he's I told him that there are also these issues, and so he wrote here in Brazil we blend ethanol with gasoline since the middle of 20th century. On average, between 1945 and 75, we practiced E7, that means 7% ethanol in gasoline. And then after 1975, we have never had pure gasoline anymore. Okay, and on gas stations, either we had E10 or E100. E10 means 10% ethanol, or E100 means 100% ethanol. Okay, and no more pure gasoline. The quantity of ethanol mixed always increased. So every year they kept increasing the percentage. Okay, and today we only have two options: E100, that is 100% ethanol, or E27.5, which is 27.5% ethanol. Okay, and they say that they have no problem with blending and using it, and that's where they have introduced these flex engines, flex cars. So the engine can basically operate either on gasoline or on ethanol. So now in India, there's a lot of pressure on automobile manufacturers to also start making flex cars, especially since up till now there's no problem because what you get in the petrol pump is typically about 10% ethanol, what you buy. And I verified that recently. I went to a gas station and asked how much ethanol is there. They told me 10%. But the plan is to have something like 20% within by 2025. And so people are getting a bit worried that will it spoil my car if you don't modify the engine. Okay. Now, so he wrote that, and I thought that I said that absolutely Brazil has led the way, and I thought that it will be nice if there is a documentation within Brazil of whether they encountered any difficulties along the path, which has led them to even introduce 100% ethanol in Brazil, and I thought that it will be good, if they can share that, so that that can be shared with all the stakeholders, all the automobile manufacturers and things like that. But I did make a point, when I was replying, that there are, of course, important differences between the two countries from the viewpoints of population, land area availability, and freshwater resources. Okay? These issues require careful deliberation. Replication of Brazil's success story may not be that easy here. And he has in fact written back to me. I forgot to put his last email and said I totally agree. I mean, so he agrees. That you cannot compare India and Brazil. So in terms of renewable energy resource, I think you need to look at this whole area of sugarcane, with much more care. And I'm just a bit worried that we might otherwise land ourselves in some problem. So now let us try and understand, how exactly molasses is obtained, and basically it's a part of the sugar production process. All of this becomes a bit irrelevant when you are producing ethanol from sugarcane juice, but because we have largely produced it from molasses all this while, it's very important. And even now, because we produce something like 30 million tons of sugar, so all that molasses obviously is also converted into ethanol. So it's not as if ethanol will only be produced from sugarcane juice. It will be produced from this also. So what happens is that it's a very tricky operation. When you crush the sugarcane and you take out juice, you have to act quite fast, because otherwise what will happen is that there will be an inversion process, and so sucrose will not necessarily remain as sucrose. So you have to prevent that, and so what has to be done is that the juice is has to be clarified and boiled, okay, and you also need to, because the juice is quite turbid, so what first people do is they add some lime to it, okay, and along with sulfur dioxide, SO2, and I'll show you what is the role of SO2, and all of that helps to coagulate all the suspended impurities. So those then fall off, and you get a very clear juice, okay, and then of course the juice is further heated, okay, and because the juice is typically got about, say, around maybe about 15% of sucrose, and we need to get to a point of about 60% before the crystallization of sugar begins. So you have to evaporate large amounts of water. Can anyone tell me what is the source of energy that is provided for evaporating water? Where do you get the energy from? Well, you get it from the bagasse, okay? Because after you have squeezed out the juice, the rest of the material that is left, is effectively lignocellulosic biomass, bagasse. And so that has got very high calorific value. So they burn it, okay, and that generates the heat, which is used in all of this evaporation process. Okay, but bagasse also has a lot of other uses. So it would be a shame if all of it is just burned and converted into CO2 and heat. So obviously there will be cleverness in seeing how to reduce, the usage of bagasse for this sugar production process. And I'm not going to go through this scheme. Maybe you can look it up, later on. But obviously you can see bagasse, all right, and steam generation, okay, power generation. So all the energy is coming from that, okay, over here, right? And as I told you, I mean, what you do is that you evaporate once, you get one crop of sugar, then you take out the sugar, you get a mother liquor, continue with the evaporation, you get another crop of sugar. Now, obviously, the grades, the quality of the sugar is not the same for all the crops, and that's why you don't take it out all at one go. You take it out separately, okay, and then finally you'll end up with basically white sugar, on the one hand, okay, and then on the other hand, you'll get your molasses, okay, and you can see it's written B heavy. This is molasses, okay, which is further treated, and then finally you'll get C light molasses, okay, and finally you'll see over here it's written distillery. So the molasses, the final molasses, is what goes into the distillery, okay. Now, sulfur dioxide has a very important role in sugar production, okay, and obviously it will affect the properties of the molasses also. For one thing, sulfur dioxide is used to maintain a pH, because SO2 is acidic, it forms sulfurous acid, okay, but sulfurous acid is a weak acid, and it helps to bring down the pH to about 5.5. Now it is, in our country, of course, all the sugar is produced from sugarcane juice, but in Europe, for example, they produce all their sugar from sugar beet, and the beet cells have a fair amount of pectin, and pectin is basically seems to create some kind of a problem, in the sugar processing plant. So what they try to do is to prevent the extraction of pectin, at the time that this juice and etc. is, the pulp is being pressed and things like that. Okay, so that's really the what is done by SO2. The second is that SO2 is a biocide, and it actually inhibits the life cycle of some of the bacteria which can promote side reactions. Like, for example, if you're not careful, sugar can be degraded into lactic acid. In fact, lactic acid is a important product from a sugar refinery. Okay, but that's provided you are aiming to make lactic acid. Okay? But if you are not, and if your target is to make sugar, then you obviously want to avoid production of lactic acid, and so that is done with the help of biocide. The third is that when you have got reducing sugars, I mean that is what is used in fermentation. The reducing sugars, of course, have carbonyl groups, and what that does is that the SO2 reacts with the carbonyl groups, of of the sugars, glucose and fructose. And if you don't do that, then when you are reaching a very high temperature, because the when I'm extracting sugarcane sugar and all into my juice, some of the proteins also get extracted, amino acids particularly. Okay, and those amino acids otherwise can react with sugars, the reducing sugars. Okay, and it can make the whole juice completely black. Okay, and that's known as the Maillard reaction. Now, by adding the SO2 and basically ensuring that it's reacting with the carbonyl, you inhibit the Maillard reaction. So your juice does not become colored, strongly colored. Because if it did, then it would affect the quality of your sugar and also the molasses. It would develop a terrible color. Okay. Now, let me also tell you, it's interesting that the Maillard reaction is also put to advantage in some applications. Like, for example, when you're roasting coffee, and we know that when you brew coffee, you get a very dark liquor, and people like that. Coffee looks nice and almost like a black colored dark liquid. Okay, strong coffee. Okay, now that is because the Maillard reaction is actually promoted during the roasting of coffee. But we don't want that for sugar because sugar is a white substance, so you kind of try to keep it as pure as possible. Now, when you take out the sugar, then this is that sea molasses which I was telling you about. This is the source of a huge amount of ethanol, even now, because you will produce molasses when you are generating sugar. There's no getting away from that. Okay, and that molasses will be converted into ethanol. So it's important that we understand the composition of the molasses. Okay, molasses has got, it's a liquid. Okay, but it has got very low water content, and the total solids in molasses is around 80%. So this is a molasses analysis which was sent to me by the Somaya distillery. Okay, and they've remarked to be a low, means that the solids is low, means it should have been around 80 to 82%. Okay, so just bear that in mind. Obviously, because it's low solids and so much of a low water and so much of solids, the specific gravity is very high, 1.43. Okay? And it's extremely viscous. We have not talked about viscosity in this plot. It's a very viscous liquid, even more viscous than honey. And so it's not easy to process it. And so, in fact, you'll find that they have to dilute the molasses with water before the fermentation process. Okay, the pH is around 5. Now the other thing about molasses that you need to know is that sugarcane juice, apart from sugar, also has a lot of inorganics, primarily things like potassium chloride, and that is coming from the fertilizer that we apply in the field. The sugarcane crop takes in a lot of the potassium, from the fertilizer, and it ends up in the juice, mostly in the juice. Okay, and obviously, when I'm making sugar, what am I doing? I'm continuously concentrating the juice, and the finally what I'm recovering is the sugar. The sugar does not have any of these inorganics, so the inorganics keeps building up in the molasses. Okay, and you can see almost like 10% by weight, is this inorganic. Now this is very important because if you have got too much of inorganics, salts in your fermentation broth, then it inhibits the action of the yeast, and it will not ferment. Okay, so and that's one of the reasons why you have to dilute the molasses, and bring it to a level where the bugs can act. Of course, these are all the big advantages of when you are producing ethanol directly from sugarcane juice, you don't have these problems, but as I said, I mean, molasses is going to get produced every time you are producing sugar, and so you have to worry about these things for at least that part from which you are using to make ethanol. Okay. Now, the total reducing sugars is very high, close to about 50%. Why? And that's the reason why you are using it for making ethanol. Beyond the point, even if I've got sugar, it does not crystallize out. Okay, and so it just stays there. Okay, and that's why it's so rich in sugar. And the sugar composition also, you can see that there is sucrose, there's glucose and fructose. Now usually this is not the composition in sugarcane juice. The glucose and fructose components are relatively less and sucrose is more, but because I've taken out the sugar, so most of the sugar has come out, and these things proportionately now become much higher, these amounts. Okay. Now, another thing to remember is that the fermentation of sugar not only produces ethanol, but it also produces a range of other organic compounds which also inhibit the fermentation process. So if these things build up a lot, then there can be a serious problem. Okay, and you can see that these are all in ppm values now. This is ppm. This is all percent weight by weight. Okay, so you can see that acetic acid is about 3000 ppm, propionic acid, butyric acid. All of these things are formed, and they are inhibitors of the ethanol producing fermentation process. Okay, just again make a note of this. Now, there is also some free calcium because we use lime, in the process of clarification of the juice, to flocculate out all the solids. And so that is there. There's a small amount of suspendable material that is still present. Okay. And so, I mean, the composition is quite complex, quite a bit of also free nitrogen. So what it means is that after you have got ethanol and you can take out the ethanol, it's not a bad idea actually to make use of the rest of the material as a fertilizer in the field, because it's quite good. It has good value in the field, and also you get back all these inorganics which are basically the fertilizer constituents. So it's like it can be recycled in the field. Okay, but there are problems also. Now, note also that there is a high bacterial count, in this molasses, and so if you have this, then it can compete with the fermentation process. So you need to get rid of this. Okay, so before you can start the fermentation with yeast, all of these things have to be basically taken care of. All right. So the main processes, in making ethanol, first is that now, whereas when I'm producing sugar, I want the sugar is a disaccharide of glucose and fructose, but when I'm making ethanol, I actually don't make it with the sucrose. The sucrose is hydrolyzed to the monosaccharides, so it becomes glucose and fructose. Okay, and that is done by an enzyme called invertase. Okay, and so I've got my monomers, monosaccharides, and it is the monosaccharides which are fermented to ethanol, by a yeast which is known as zymase. I mean, there are different types of enzymes that are available, and typically when you do this, you have about 12 to 15% of total reducing sugar, which means that you have to dilute the molasses by roughly about you have to make it 3 times, as dilute. Okay, 3 to 3.5 times. and you have to bring it down, right? So that's the level. Now, you can see the delta H value. So obviously it is an exothermic reaction. So you also need to have heat exchangers, which can remove the heat, because temperature also has a very crucial role on the fermentation process. So that's also important to make a note of. Finally, all of the glucose does not become ethanol. I'm not even talking about all of the stuff which is already present in the molasses. I'm talking about the sugars which are fermented to ethanol. There is one side reaction, which is this, and it converts, the mono saccharides into fusel oil. Fusel oil is basically a long chain alcohol, something like a C5, C6 kind of an alcohol, right? And it also forms some aldehyde, okay? And that aldehyde is reasonably volatile, right? So this is volatile, but long chain alcohols are not very volatile. Even ethanol has a boiling point of about 78. Now, once you go to propanol, butanol, pentanol, the boiling point is high. Okay, but we'll see something interesting about this. Okay, now, so this is typically the scheme for producing ethanol. You are taking molasses, okay, and you can see what happens is that part of the molasses is actually being used to grow the yeast, which I need for my fermentation process. And any growth of these microbes, obviously I require nutrients, and so that is provided by the molasses. Okay, so I take a part of my molasses, but remember it had a high bacterial count, so I sterilize it. So I have to do a steam sterilization. You can see steam is being put, and so it's sterilized. Okay, and then it is basically being fed with some nutrients and the yeast culture. Okay, and then I'm multiplying the production of yeast. Okay, and then I have the yeast storage, and this also will generate carbon dioxide and water as byproducts of the yeast production process. Okay, now, so this will take up a small amount of the molasses, but the bulk of the molasses is being diluted here, you know, and diluted by three and a half times, as I told you, to 10 to 15%. Okay, and this is my fermentation tank. Okay, and now I am feeding the yeast into this. Okay, now you can see there is a heat exchanger here because the reaction, as we said, is exothermic, so I need to cool it, so I have a heat exchanger here. Okay, to cool down the material. All right, now I also have a scrubber because when it is fermenting and forming ethanol, just like here, any fermentation process will also generate carbon dioxide because the bugs are also respiring. There is a respiration process that takes place. Okay, so there is CO2 production, and there is also some amount of vapors, that will come out, and then these are scrubbed. Okay, now I'm doing a scrubbing over here and then allowing the CO2 to escape. Okay, now then what happens is that after my fermentation is over, I feed it into what is known as a beer still. Okay, now after the fermentation, like we started with 10 to 15% sugar, typically I'll have about 6% ethanol, in my fermentation. Now, all of you who have had beer, you will know that beer typically has about, something like 4 to 6% of alcohol, right? And so what people also do is that you can use this actually to make beer, you know. And so I don't have to necessarily then remove anything. I just basically can convert it into beer, okay. Or if I'm trying to make ethanol, you know, then I have to do several things. I have to concentrate my 6% ethanol, right? So what happens is that this is known as a beer still, right? Where I am evaporating, okay? I'm stripping of water. So obviously, I'm basically trying to distill out my alcohol, but my alcohol doesn't come out as neat alcohol, you know. It comes out as 50 to 60% alcohol, and then there are also, I told you about those aldehydes which are formed. Those aldehydes also come out. So I've got alcohol plus aldehyde, you know, coming out as in my vapor stream. Okay. And now I've got my liquid here. Okay. And once I have stripped off all my alcohol, you know, this mass over here, which is known as slops, all right, there will be some solid, some liquid. I mean, you have to separate them out, and the liquid is what becomes then what is known as spent wash. Okay, and we will talk about spent wash. It's still got unreacted sugars, you know, because all of the sugar doesn't react. Small amounts will remain, you know. All there'll be propionic acids, all those acids that we talked about, all that stuff will end up here. Things which are non-volatile. Okay? And my volatile, my alcohol with some amount of water, and my aldehyde is basically coming into a second still. Now here I'm doing a rectification. Means I have got a fractionating column, and so my aldehydes are quite volatile, you know. So I can now do the fractional distillation in a way that the ethanol is not coming out, you know, but only my aldehyde is coming out. Okay, so I collect the aldehyde, you know, and that aldehyde is sold because the aldehyde fetches a has a market. Okay, now once I've removed the aldehyde, what happens is that the higher alcohols, you know, the fusel oil we talked about, you know, the higher alcohols, most of it, almost the entire, not the entire amount, a sizable amount will start separating out from the water. Why? Because the higher alcohols are not soluble in water. Okay, so they will form a separate layer. So what I do is that I have a decanter, you know, and I take out fusel oil, which is my higher alcohols over here, and then I've got my rest of the stuff, you know, which is basically free of the mostly free, okay, of the fusel oil, but not all. So it goes into another column which is known as a recycling column. Okay? Now here something very interesting happens. Now, what would you expect the boiling point of ethanol and butanol to be? Which would be higher between ethanol and butanol?
Butanol.
Yeah, no, you're absolutely right. But you know, very interestingly, what happens is that over here, when I distill, the butanol actually comes out, you know, at a lower temperature. Can you tell me why that might happen? Although, you know, I know that ethanol has a lower boiling point, but it is the butanol which tends to come out. Well, what happens is, you know, ethanol, because there is still water, na? We had 40 to 60% ethanol. So there is quite a bit of water still here, you know. So what happens is that when I, you know, when ethanol and water are there, ethanol and water form very strong hydrogen bonds. Okay, the hydrogen bonding between the two is very high, so that prevents the distillation of the ethanol. You know, it strongly hydrogen bonds with the water, and so it is the higher alcohol which will volatilize. That doesn't form strong hydrogen bonds with water. You know, so that comes out. I again feed it back into the still, and it this whole process comes out again. It will go for decantation, and ultimately all of the fusel oil will end up basically decanted. So it is just coming out here, and whatever was left here, I'm feeding it back into this still. All right. Now, then I keep evaporating, and I'm taking out almost pure ethanol, and what I'm getting left over is again my water, which is now depleted in my ethanol. Okay. Now, ethanol has a property in the presence of water that, you know, uh, when I when I evaporate, I cannot make ethanol more pure than 95%. Okay, I'll have 95% ethanol and 5% water. Okay, and can someone tell me why that is the case? What happens? Why can I not get pure water, pure ethanol, 100%? Ethanol and water form a constant temperature azeotrope. Okay, and because of that, both will come out in that composition, that 95% ethanol, 5% water. So, but if my objective is to, let's say, make alcohol, like all these whiskey and all very high alcohol content drinks, then in fact, if anything, I take that 95% ethanol and I have to put some water into it and make it of the right composition. Or 95% ethanol is used as an industrial solvent. It has got a very high demand. Okay, so the 95% ethanol will go either for as an industrial solvent, or it will go into the production of liquor. Okay, now what I also do is that, the ethanol also has use in many other applications, like rubbing alcohol, or rectified spirit, which people use. Now that spirit you are not supposed to drink. Okay, so what has to be done is you have to poison that ethanol, so that nobody is drinking it. Okay? And so people, that is done by adding a solvent like methanol or pyridine. These kinds of solvents are used in small quantities, and they're mixed, and this is what is known as denatured alcohol. This is used by hospitals. Hospitals have a high demand for denatured alcohol. Okay, and then if I want to use it as a fuel for my vehicle, okay, now there I cannot use 95% ethanol, because that 5% water will completely corrode my engine at high temperature. So I have to get rid of that water. So there are ways of breaking the azeotrope. One way is through addition of benzene. If I add benzene and make it a ternary system, that is benzene, water, ethanol, okay, it breaks the azeotrope, and I can then distill out pure 100% ethanol. Or I can use other methods to separate out the water, and I'll show you. Is the scheme very clear? Has everybody understood the scheme? Anyone who has not understood? Now, these things over here are known as reboilers. It's basically to maintain a reflux. Okay, and I mean, So I obviously am heating and cooling. I have to heat something, then in the condenser I'm cooling. Okay, I'm recovering the latent heat. So basically there is a reflux that takes place. Between the stream that is falling down and the stream that is going up. And so that is I'm achieving that through the reboiler. Okay, and so this is my total scheme. Okay, for basically producing ethanol. Any questions from anyone on the scheme? Have you understood it?
Yes, sir.
Okay. All right. Now, I'm not going to go through all the details, but there I've shown you schematically, right? But in each of these steps, the details of what is being done, right, is basically mentioned. Like molasses storage tank. Molasses liquor obtained as byproduct. Molasses heavy viscous material. Sterilization tank. You have to sterilize. And then you have to basically produce yeast. The yeast cultivation tank. You have to dilute the molasses. You have to scrub off the CO2. And other things that are released during fermentation. Whatever comes out into the gas phase. Okay, there'll also be some entrained ethanol, so you will also need to take out that, because you can't release that into the atmosphere. Okay, and so this whole thing is done. Now you'll see over here, you see, I mean, molasses has to be, as I said, diluted uh, to a concentration of 10 to 15% from around 50%. So you need fresh water, to carry out this dilution. Now, this is interesting that on the one hand, when you are producing sugar, you have to concentrate sugarcane juice, right? And you spend a lot of energy, a lot of bagasse has to be heated to evaporate the juice and to take off water. And on the other hand, the molasses which I'm finally getting, I have to dilute it with water. Of course, the water balance is very different because molasses by weight is only 5% of my initial sugarcane juice weight. So it's not as if it's a very large amount of material, but nonetheless, it requires water. Okay? Now, this is something that was invented in ICT, all right? It's also been granted a patent, you can see last year, okay? Indian patent number so and so. And let me tell you, what actually is done. Now, when you are taking a course, one is that you should know, of course, what is being done up till now. That is very important. But all the time in your mind, you should think, how can I improve it? Can I make things better? Because renewable energy resources, doesn't mean just keeping on producing more and more renewable energy. Most important is how to conserve energy. How do I save energy? First, do that. Don't just keep producing more and more energy. I mean, first you conserve whatever else you require. Of course, you produce more renewable energy. Let me tell you what is being done. I told you that the molasses has got high amount of solids, high amount of inorganics. Okay. Now, if you measure the osmotic pressure of the molasses, it is 191 bar, means around 191 atmosphere is the osmotic pressure. Okay. Now, if you take the sugarcane juice, at the inlet, where, or the sugarcane juice which you are concentrating to make sugar, its osmotic pressure is around 10 bar. So this has got a much higher osmotic pressure. Now, when I've got a high osmotic pressure, it means that it can spontaneously suck out water, from, that is the process of osmosis. All of you have learned that I have a semi-permeable membrane. Okay, on one side I have a solution which is a has a high osmotic pressure, like sodium chloride. On the other side, let's say I have water, and the water will permeate across my membrane and will go into my sodium chloride. Okay, so likewise over here, this is a membrane module. Okay, and there are many of these fibers. Okay, and I've shown you an electron microscope of one such fiber. Okay, there are many such fibers. Now what you do is that you pass the juice through the inside of this fiber, through the tube, and from the outside you circulate molasses. Okay, now water will go travel, not water only, not the solutes in the sugarcane juice. They will be retained in the juice, but the water will pass through and it will end up diluting the molasses while it itself gets concentrated. Okay. And so, by this kind of a process, I don't want to go into all the details, one can convert, let's say, a 14-degree Brix juice into something like a 16-degree Brix juice, and you can actually reduce the evaporation load of water. I mean, actually, it's much more. It is about 14%, the total amount of water from the sugarcane juice that you are taking out. Okay. Secondly, by this process, because your molasses is also getting diluted, the ratio of the molasses and the juice was taken such that the molasses gets diluted by about 3 times. Just what you need, to be able to carry out the fermentation. Okay, and so effectively what you have done is that you have, without investing much of energy, using a spontaneous process, you have been able to concentrate, partly dewater the sugarcane juice, and you have been able to simultaneously dilute the molasses, and so you have saved energy. So I can save about 14%, 15% of biogas, which otherwise I would have unnecessarily used to strip off water. I don't need to do that. I can do it by this process. Okay, is this clear to you? The process?
Sir, hello, sir.
Yeah,
Sir, I have a doubt. So, the tube that you mentioned, the single hollow fiber tube that's shown in
yeah,
the SEM image,
yeah.
it's inside the FO module, right?
Yes, and these are, each one of these is that tube.
Sir, then, like, if this is organic fiber, if we are talking about,
Yeah.
is it able to sustain that high level of pressure of 10 bar or even?
Very interesting. You see, this is not hydraulic pressure.
All
This is
right,
osmotic pressure.
right.
Your hydraulic pressure is nothing. It's under almost like atmospheric pressure.
Okay, okay.
Okay.
Yeah,
You
yeah.
are only making use of osmotic pressure.
Right, right, right.
Whereas, your question is a good one. Like if I do reverse osmosis, you
Right.
know,
Yes, sir.
there I have to apply hydraulic pressure.
Hydraulic pressure. All
Huh.
right.
And that hydraulic pressure which I apply is about, something like, say, if I'm doing seawater desalination, I will apply 50 to 100 bar, 80 bar pressure.
Yes, sir.
And whereas the molasses, has 190 bar pressure.
95.
And yet, almost silently it's doing its job. You won't even notice it.
Right. That's all.
Got it?
Yeah,
Huh?
yeah, yeah. Thank you, sir.
Okay, and then actually the proof of the pudding is in the eating. So in fact, this molasses which was diluted was directly sent for fermentation. By, and these people have provided the data, and they get absolutely at par performance. That means if I take molasses and use fresh water and dilute it, and if I take molasses and by forward osmosis, if I dilute it, both of them give pretty much the same result. Okay, huh? There is no difference, and you can see is more or less. You remember we said about 75 to 80 liters of alcohol per ton. Okay, that's basically what it is. All right. Okay, but let me also show you or tell you about something which you need to know. Okay? Now, this company whom we are working with were very excited when they saw all this. And look what they say. We really need to commercialize this unit operation as soon as possible. Right? We can come for a meeting, and all that is great. Okay, but then what happened was that because the government changed its policy and is now allowing sugarcane juice to be directly fermented to ethanol, right? So what companies are doing is that when the sugarcane production season starts, that's the time when they get sugarcane juice. Okay, so they take that juice, and they are directly fermenting and making ethanol. Not all the juice. Some juice they are producing sugar, right? So they are producing sugar and they are producing ethanol during the season. Okay, and because molasses has got very good keeping property, so what they do is they have developed huge storage facilities for molasses. So when the season is over, the sugarcane production season and making sugar, then they start fermenting the molasses, all right, to make ethanol. But now I don't have sugarcane juice. Okay, so the entire, work on using sugarcane juice, concentrating the juice and diluting the molasses, which worked so well, okay, and which would have been the technology which people would have jumped upon, till about 2 years back, today is not true because I don't have sugarcane juice and molasses together. They will always keep the molasses for the off-season period. So now a separate technology is being developed, where whatever is the aqueous stream that is formed when molasses is being fermented in the off-season time, okay, and which I told you is spent wash, so, and there's a huge problem in the disposal of spent wash, So basically, the technology is now being reoriented, to use spent wash and molasses, basically to achieve a similar objective, So the important point that I'm trying to make for you, and I've written it down, things have changed since this correspondence. During the regular season, ethanol is produced from juice and not from molasses. And what else is produced? Sugar. Molasses is used off season, but there is no juice then. An alternative opportunity has been identified and being worked upon. The important point is that technologies have to evolve in line with changes in priorities and production logistics. So if you think you will just hold on to one invention that you have made and you will gloat over it and be very happy, forget it, it can become irrelevant and obsolete, as has happened in this case. Okay. Now, so I'm not going to go through. I've already explained to you the process, but the details for each of that, beer still, aldehyde still, decanter, everything, all right, is mentioned in detail here. And also, let me tell you that I have taken this material from one of the NPTEL lectures, and I will forward to you the NPTEL lecture. Okay. Now, if you don't want to use benzene, because benzene is a carcinogenic substance, you know, and to make your absolute alcohol, although that absolute alcohol is going into cars, you may still not want to use benzene. There is another way in which you can make absolute ethanol from 95% pure ethanol, and that is by using what are known as molecular sieves, zeolites. And these are a particular zeolite, it's called zeolite 3A. This is not the zeolite that is used in petrochemical refineries for catalysis, but it's a zeolite 3A, which is a water adsorbent. And so now I don't have an issue about azeotrope. The zeolite is picking up the water, and it is leaving you with absolute ethanol. So this is the alternative technology. So you will also find that for something there can be 2 or 3 or 4 competing technologies, and it is for you to decide, depending on all the situations and circumstances, what exactly you will choose. Now, let me tell you that I also showed you that you have to dilute the molasses by 3.5 times, and then you basically do the fermentation. But what it also means is that the ethanol I get, will be just about 6% ethanol, 6 to 7%. And so, I've got several problems. One, that I need huge fermentation tanks because I have to process so much of material, by volume. Okay, so the tanks, the fermentation tanks have got to be very large. And secondly, when I'm stripped of the ethanol and I'm left with an aqueous phase, that aqueous phase, which I call as spent wash, by volume is so large, that it becomes a huge problem to manage. And all these distilleries, biorefineries are grappling with this problem, and they are up in arms, about how to really solve this problem. Now, if, for example, I could have fermented molasses, okay, with say, suppose instead of diluting it 3.5 times, I dilute it only twice, so that I get something like 25% sugars, then I might be able to make ethanol with about 12% concentration. And that will increase my throughput. That will also reduce the amount of water stripping that I have to manage later on, etc. So, another, just like I showed you, one technology which is being evolved. This is another. Now, there are certain yeasts which have been developed, which can actually carry out the fermentation, right? Even with something like close to 20% of sugars, why 20, even 25% has been done, right? And so I end up with something like, a much higher volume of ethanol, okay? Now, ethanol is being produced by the yeast, but ethanol is toxic to the yeast, So this yeast, Saccharomyces cerevisiae, which has been made ethanol tolerant, can tolerate these higher levels of ethanol, and also the higher levels of sugar, etc. And so I can, if this were to become technology tomorrow, it would have a massive impact, on the entire industry in terms of the saving of capital cost, etc. Okay, and like this is another thing. Different kinds of strains, and some of them could be also genetically engineered strains. Okay, which have been developed, right, and they are able to now, basically make ethanol or produce things with ethanol at a higher concentration. Okay, it's still not so good, but I know that people have reached close to about 12% of ethanol. They don't always share their waste data. You asked a question, I think, no? About uh, we can make glacial acetic acid by cooling acetic acid below water's freezing point and removing the water as ice. Yeah. Why can't this be applied for water removal from ethanol? It's a very, very good question, you know, and you might want to try it out. Okay. Uh, what may happen sometimes is that where you have to be careful is that if the ethanol gets entrapped in ice, you know, then you could have a problem. Okay, because you don't want to lose any ethanol in ice. Okay, so you have to make sure that there is no entrapment, right? But otherwise, it sounds like something which is feasible, you know, and you might want to try it out. Yes, you're right about acetic acid. And in fact, there are other cases, where we had recommended freezing to the company, right? Like, for example, sodium sulfate solution, you know, and they have in fact done that by freezing. And the advantage is that the latent heat of fusion, you know, is much lower than the latent heat of vaporization. And so you can gain. But of course, there are also things like, when I'm evaporating something, there are multiple effect distillation, you can do. And there is some amount of gains that you can get from heat integration, which is much more difficult to do for freezing. So you'll win some, but you lose some. But overall, there could be a gain. But it could be a great project to look at. By the way, let me tell you another thing that I've suggested to them. Okay, and that experiment has not been done yet, and it was I showed you this salt. Okay, that sodium chloride, and you had a problem today. All right, on how much water you have to evaporate from seawater to make salt. The question I had was, what happens if I just take sugarcane juice and let it solar evaporate? Okay, just like you are evaporating seawater, can you evaporate sugarcane juice? Now, normally it's difficult because the sugarcane juice can get inverted, or and you cannot put harmful things for sugar production. Okay, you cannot put such additives. But if your objective is to make absolute ethanol, where it doesn't matter, it's going to go into my vehicle, I might be able to put some inhibitors which can inhibit the growth of bacteria. It can, it can inhibit the inversion process, and I might be able to just do solar evaporation. And you might actually be able to use similar kinds of approaches to making salt, you know. And they told me that they will try it out, I don't know whether they have tried it out yet, but maybe you can, an experiment can be done in ICT, or somewhere nearby, and we can see, if we can just make concentrated sugarcane juice through solar evaporation.
Yes, sir.
Have
Thank
I
you.
answered your question?
Yes, sir. Thank you, sir.